Welcome again. Let me share. Okay, so I don't know why the problem with the camera maybe. Okay, so now we have this one. Okay, so here we have the strain energy now. U is equal to 0 to L integration U of L, this one, times dx, which is equal to, this is for the unit length. That's why we should making the times of the dx. Now we will have the half. Okay, so integration from 0 to L EI d squared v over dx squared all squared dx. Okay, this is the strain energy. So potential energy of applied load. Okay, now V, this is the potential energy minus the integration between 0 to L, the P of X load times V of X. This is the displacement times dx minus, if we have this is the distributed load, this is the concentrated force, and this one is the moment. 1 to number of force Fi, V of Xi minus 1 to the number of the moment Ci dV Xi over dx. So potential energy, the yellow one, it's too important. You should know this one always. Pi is equal to U plus V, which is the strain energy plus the potential energy of applied load. It is equal to half. We say the integration 0 to L EI d squared V over dx squared. So L square, so the dx minus the applied load, these applied loads also. Okay, as general, maybe we don't have moment, maybe we don't have distributed load, just only we have this one. Okay, it's not always you have all types of the loading. Potential energy is a function of Vx and slope. So the beam is in equilibrium when pi has its minimum. When we say minimum value, this meaning that del pi over del v, okay, which is the displacement, should equal to 0. So now we have Rayleigh-Ritz method. So assume that deflection shape, we have C1F1 plus V to C2 VF2 plus blah blah to CNFN. So unknown coefficient, we have constants CI, C1, C2, okay? And now function F of I. So deflection curve, we have V of X, most satisfied displacement boundary condition. Now, obtain the potential energy as function of coefficients. So this is the potential energy is equal to strain energy plus the potential energy comes from the applied loads. Okay, this one, V. Applied principal minimum potential energy to determine the coefficient. Del pi over del C1 is equal to del pi over C. Del C2 is equal to del Cn to equal to 0. For example, We have the simply supported beam. This is the very important example. We have distributed load P naught. We have E, I, and L. Okay, this is the distance between the support and the support. So, and here assume deflection curve is equal to C sine pi x over L. So satisfying essential boundary condition, this is important. So how can we satisfy this one? So if x is equal to 0, if x is equal to 0, what's the sign 0? What's the sign 0? Sign 0 is equal to 0, right? So this meaning that we have the deflection here 0. If we have L, the distance between the first support to the second, the next support, this is the L. So if we put the instead of XL, L over L, so cancel each other. So sine pi, what's the sine pi? Sine pi also is equal to 0. So this meaning that this function is satisfy the boundary condition. So now we have strain energy. We say that U is equal to half of 0 to L EI d square V over dx square, this all square dx, okay, this is the U. And we have potential energy of applied loads. So it is, we just only have distributed load. We have minus integration 0 to L, P of x, Vx dx. Okay, now, from the strain energy, this is equal to, if we making the second derivative, this is also homework. This is the homework. I will open in the Moodle this panel or this exercise. So you should making the derivative dv over dx of this function, which is equal to c times pi over L cosine pi x over L. Now, the second derivative you should make, the second derivative also is equal to c pi square over L, and now minus, because the derivative of cosine minus sine. Okay, this is square sine pi x over L. So, and you should put this one here. U is equal to half 0 to L. So EI constant outside. Okay, and we have C pi square over L square and sine pi x over L. Oh, this one square dx. Okay, so after opening this one, EI over 2 integration 0 to L will be C square. Okay, this is the first one. So we have C square. We have pi to the power 4. We have L to the power 4. We have sine square pi x over L dx. And how can we integrate the sine square? You should have the relation to convert to the double of the angles. For example, 1 minus 2 sine pi of x over L, like this one. Okay, this is that's why this is the trick in the integration way. So this is the important to solve this sine square. Now, okay, this is important. Please try to solve this one and submit to me. And also it's very important in the exam. Now, potential energy of applied loads, no reaction forces. So we have P, which is minus 0 to L, P of x, Vx dx. So is equal to minus. So P naught, this is the P naught, okay? So times the V, which is C sine pi x over L dx. Now just only integrate, which is the integrate of the sine. It is equal to minus cosine, okay? So, and times of L over pi. So after then you should, this is very important. Let me solve this one. Okay, this is very important. How can we get, okay, after making this substitution, so is equal to minus what's the integration of sine? It's minus cosine. It will be positive p naught times c times cosine. We say cosine, and here we need the pi over x. So then invert this one L over pi, okay, to get the angle constant here, pi over L, between 0 to L, so is equal to P naught C L over pi. This is the constant. Now, what is the cosine? The upper one, L over L, cosine pi is equal to minus 1. And also we have minus the other one, is equal to, what's the other one? Cosine 0 is equal to 1. So at that time, we can say is equal to minus 2p naught CL over pi. Okay, this is very important to get using hand. Okay, potential energy is equal to this, the pi is equal to U plus V. So here we have the U, okay, this is the U, okay, and this is the V, just only making the summation, okay. So minus, this is, if this minus, this also minus. If this plus, it will be plus, the same, okay? Because we have plus times minus minus, plus times plus plus. Okay, this one, plus times minus minus. So EI pi to the power 4 c squared over 4L cubed. Now we have the derivative of the potential energy, this one, of this potential strain energy with respect to the constant, okay? So we will have the derivative, this one, EI pi to the power 4 over 4L cubed, this is the constant, times c squared, it's the 2c, okay? So 2 goes with the 4, it will be 2, okay? That's why this 2 and this one just only one order. This is the second order, it will be one order less, this one. So minus 2p naught L over pi. So what's the derivative of c? It will be 1, okay? This 2pl naught over pi is equal to 0. At that time, we can say c is equal to 4. So after making the manipulation, 4p naught L to the power 4 over EI pi to the power 5. And just only we find this constant. This is the important. Now the deflection curve is available to find any deflection at any point. Okay. So exact, and if we compare with the approximate deflection at the center. So if we substitute here, instead of x is equal to L over 2, L over 2 sine pi over 2 is equal to 1. So at that time, we can say that it is 4p naught L to the power 4 over EI pi to the power 5. So pi to the power 4 over 4 pi to the power 5, what's this value? Let me say 4 divided by the pi to the power 5. Okay. 4 divided by pi to the power 5 is equal to 0.01307. Okay, this one. So this meaning if we making that multiplication, if you want to making the multiplication, this one. If we working 1 over value, you should say 1 over x like this. It will be 76.5. Okay. So it is P naught L to the power 4, 76.5 EI. So, and the exact one from the strength of materials you can find, or from the handbook or the manual of the steel, you can find this deflection also. It is a good table to find the deflection. P naught L to the power 4, 76.8 EI. So approximate bending moment and shear force. Now moment is equal to EI d squared V over dx squared. Now after making the d squared V, this is the V, this one, this is the V C, and after making the C here, okay, substituting, so we can with this one C pi the derivative, second derivative, pi squared over L squared sine pi or x over L. Now we can get this one. Okay, this is the first one. So the second one, V of y minus EI d cube V over dx cube. So this is also, it is the important to know this one also, and making the homework with the previous one. EIC pi to the power 3 over L to the cube cosine pi x over L, and this is equal to this value, okay, by V of y, which this is the shear, and we have the exact solution. Try to find the exact solution from the steel manual. You have some tables to find the, for example, simply supported with distributed load, with a partial load, with a concentrated load. You can find the displacement. Okay, so and this is the moment, and this one is the shear. It's available. Just only making the substitute of the x at any value at any position, you can find the moment, shear, and the displacement. So you can find these equations, the exact one in the table of the manuals of the steel. So try to make the difference shape, get this plotting from the MATLAB. You can use the MATLAB, or you can use any finite element, maybe if Abacus, Nastran, ANSYS, any other software. You can making the difference between the V of x over V maximum, so which is the normalized to 1, okay? And here we have the x also normalized, okay? We have the maximum one is the 1, okay? This is the error increase here. So bending, we can see the bending. This is the bending, like the WL squared over 8, right? So this is the bending moment of m of x. And here we have the x values. If we have, for example, is equal to 1, so we can find that this is the exact one, and the dotted one is the approximate one. You can see the difference is very small. But it is more than the deflection. And in the shear, you can see the more error difference between the two curves, okay? So this is very important. Now we have, for example, the cantilever beam, assume deflection 1. For example, in the exam, I will give you the assumed deflection, okay? This is the important one. I will just only want to solve to get the V without any constant, to get the deflection, to get the moment, shear, okay? So here we have 1, 2, 3, 4 constants. So here we will need 4 equations to solve it. This meaning that we have the potential energy with respect to A0 with B0, C1 0, C2 0. Now, need to satisfy the boundary condition. If we have, for example, here we have a cantilever. So if we have x is equal to 0, here we have, if we have x equal to 0, 0, 0, 0, and here we have the v of x is equal to a. This is not logic, because v here should be 0, okay? So here, let's making the derivative of this one with respect to x. It will be b plus c1 plus, okay, this one. Let me write for you. Let me write for you. V of 0 is equal to a plus this one 0, 0 plus x 0, 0 plus 0. So this meaning that v of equal to 0, this meaning that we have fix it here, okay, and x. So x is equal to 0 here. So if v0, which is the displacement, is equal to 0, this meaning that a is equal to 0. Now we have another condition. We have another condition here in the fixed is the dv over dx at the 0, which is the slope is equal to 0. Okay, so after now a is equal to 0. Just only we will have 3, 1. Okay, so we have dv over dx at 0 for which one? X, let me first. It will be plus 2c1 plus 3c2x square. I'm sorry, c2x square. Okay, c1x. Okay, c1 2c1x plus 3c2x square. This is this one. Okay. So now dv at 0 is equal to 0. If we put 0, so this means 0, 0. Now b is equal to 0. What's the remaining now? Just only c1 and c2. Okay. This meaning we will need 2 equations instead of 4 equations. So v of c1 and c2 potential loads. And here we have the strain energy. Strain energy EI over 2, 0 to L for 2C1, because this is the derivative, okay? This is the dv small over dx, okay? dv small over dx. So is equal to 2C1 plus 3C2x squared, okay? So, and this is the first one, dv over dx. Now, in the strain energy, if you go back to strain energy, let's find the strain energy equation. This one, half EI over 2, 0 to L, d square v over dx square. Now, this meaning that d square v, this one. Okay, d square v, this one, d square v over dx square, it will be 2c1 plus 3c2x square. This is 3, not 6. Please, this is 3, not 6. Okay, x square. No, I'm sorry. So 3 times d square v. Okay, d square v. Sorry, d square. Okay, d square v, it's right. So it's d square v. This meaning that we have v, this one. So dv over dx is equal to 2c1x plus 3C2x squared. And d square v over dx squared is equal to 2C1 plus 6C2. So this one, if you don't write, you can make the mistake. So this is the 2C1 plus 6C2 x all square dx. This is the strain energy. Now we have potential energy. We have distributed one, which is minus, and the direction here, it is also minus because y is up is the positive. Now we have minus. So this is the minus of equation, minus of P naught V of x dx minus. Also, we have this force F times V. Where's the V at L? Okay, V at L. And also we have that moment at the end, dv over dx at L. This is very important and too easy, this one. So, and this is equal to minus minus plus. So after making the substitution of this Vx, this is also homework, making that substitution, this one here, this one, substitution here, instead of Vx, and making the integration. What's the integration of C1x squared? It will be C1x cubed over 3. And what's integration, for example, of C2x cubed? It will be C2x to the power 4 over 4. And making the substitution after then between 0 to L, you can find the, for example, the relation, okay, between C1 and C2. And also we have FBL. What's meaning FBL? C1L squared plus C2L cubed. So minus C, this C is the moment. You can change this C as the, for example, making M or another value, C capital. This capital is a moment times dv, it's not constant, dv over dx at L, making this derivative 2c1x plus 3c2x squared, and substitute instead x is equal to L, you can find this one, okay? So this is the potential energy. This is very important to my dear students, because, for example, let me solve the first one. Minus will be plus. P naught 0 to L, okay, C1 x squared plus C2 x cubed, okay, dx is equal to Cp naught here, okay, let me do this, P naught times C1, right? C1, this is okay, P naught, this positive, okay, positive, P naught. Now we have C1 x cubed over 3 plus C2 x to the power 4 over 4, okay, 0 to L. It's very important to know that it will be is equal to P naught C1 L cubed over 3 and plus P naught C2 L to the power 4 over 4. And after making all opening this one and this one, for example, here, the first term here, the second term here, okay? Is it clear, this one? I think it's clear. Okay. So after find the strain energy, after find the potential in loads of loads, so strain energy and potential of loads, we can find the total potential energy loads, which is now we should make the derivative after making the summation, for one. So after making the summation, del u over del C1 is equal to 2EI, 2EI, this one, I'm making the summation, 2EI, 0 to L, this term, and this is equal to the first one. So this meaning that derivative with respect to C1, okay, and this meaning that C2 is constant. This is very important. After making the integration, of dx, so now the integration of the 2C1, it will be 2C1L plus 6C2 x squared over 2. So and after then, instead of x, we should substitute L. Okay. So then U over del C2, the same procedure. So we should make the integration first and then make the derivative with respect to C2. So now del pi over del C1 is equal to 0. So is equal to, this is the first equation. And this is the second equation. Also, try to solve this one manually and send to me with the homework. So solve for C1 and C2 because we will have two equations. This is equal to 0. This is equal to 0. So after trying to solve it, so you can find the C1 and C2. Is this one correct? Is this one correct? You should check it, and you should after find the C1 and C2, you can substitute in the equation of Vx and try to compare with the exact solution. Okay, so this is the curve. Also you can find so here we have 0 deflection and go into increase with the L bending moment. Here we have the exact one. The dot one is this the approximate one. Here we have the shear force. Here we have the exact one. Here we have the approximated one. So this is the exercise. Please, you should solve this one. It's too easy. L1, L is equal to 1, and here we have E, I, and P naught. Okay, so this is the deflected shape of the function. So try to solve this one. F1 is equal to x1 minus x, and the second one, F2 is equal to x squared minus x. Calculate deflection curve, bending moment, and shear of the simply supported using the two basis function. The first one, this one, and the second one, this one. Okay, so here you will need to put the coefficients C here. Okay, this is the C. Also, this is the C. Okay, so the first time you should solve the first one. For example, cx1 minus x. The second time you should solve with respect to 1. The second one should be accurate than this one because it's higher order the first one. Okay, so also we have the interpolation. So we have about 5 minutes. Let me go in the fast way. This interpolation, Riley-Ritz method, approximate solution in the finite element. So difficult to find approximation solution that satisfy deflection equation boundary condition. So make it easy satisfy displacement boundary condition. I think we will need to divide the beam using the set of elements. You have the elements are connected to other elements at nodes. Concentrated force and couple can only apply at nodes. Consider two node beam element, positive direction for force and couples, constant or linearly distributed loads. Okay, so nodal degree of freedom. Now we have each node have deflection V and slope theta, positive direction, degree of freedoms. So vector nodal, we have V1 theta 1, V2 theta 2. We have two nodes for each element. So the S is equal to x minus x1 over L. This is the S is equal to 0. This is equal to 1. So x minus x1 over L. So ds is equal to 1 over L. Okay. So this is the dx is equal to LDS. This is important. dx is equal to LDS. So ds over dx is equal to this ds over dx, this meaning that 1 over L, it's related all to this one. And we'll write deflection curve in terms of S, okay? This S is equal to 0, S is equal to 1, this maximum 1, okay? Scaled. Length L of beam is scaled to 1 using scaling parameter S. So we will not say if even you have 10, 20, 15, so we will say just only 1, okay? 0 to 1. Interpolate the deflection in terms of for nodal degree of freedom, use cubic function, a naught plus a1s plus a2s squared plus a3s cubed. Relation to the slope, we have theta is equal to dv over dx, and this meaning that dv over ds times ds over dx. So n is equal to 1 over L. dv over ds is equal to a1 plus 2a2s plus 3a3s squared. So apply for conditions at 0 is equal to v1. At this is the theta 1 dv over dx. So v at 1 is equal to v2. And this is important. Okay, v at 1. Okay, so it's equal to v2. Okay, it is not this one. V at 1 at this one. Okay, at distance 1 is equal to v2. So and if dv at L is equal to 1 is equal to theta 2, this one. Okay, so and at 0 is equal to v1. This is the shear, and this is the theta. Okay, so express for the coefficients in terms of nodal degree of freedom. V1 at 0 is equal to, this is important, is equal to a naught, this one, V1 at 0 is equal to a naught, and theta dv over dx, this is very important, is equal to the first one, which is 1 over, we say the 1 over L, this one, 1 over L, okay, because here we have S is equal to 0, just only we have 1 over L A1. Here we have A2, A naught in the V1. At the 1, if we substitute 1, we can say that the V is equal to A naught plus A1 plus A2 1 square plus A3 1 square, okay? So 1 cube, which is A naught plus A1 plus A2 plus A3, and theta is the same. It's a very easy 1 over L A1 plus 2A2 1 times 1 plus 3A3 1 square. So this is important, okay? So V1 is equal to A naught. Now A1 is equal to L theta 1. Now A2, if you have A naught, if you have A1 substituting here, so you can say A2 is equal to minus 3 V1 after substituting, minus 2L theta 1 plus 3 V2 minus L theta 2, and also you have A3, you can find it, okay? So this is the deflection interpolation continuous. And this is the V of S is equal to N shape function times the Q, okay? And this is the shape function, the N1, N2, N3, N4, N1 deflection, this is theta deflection at to the theta, okay? Is 0, 1, is 0, 0. Then L1, it will be 1. At 1, it will be 0, okay? So this is Hermite polynomials, interpolation property. Thank you so much, and I hope to find you in the next lecture. I hope to send to me your notes and your homework in the Moodle. Bye bye.
Thank you, Doctor.